Hello viewers, calculation of functions is major task in the problems of science and engineering. It is also required in many numerical techniques, some of which we have discussed in our previous lecture. If the expression of the function is provided to you, you can calculate the value of function by substituting the variable x in the expression of the function. However, in many cases it is desired to express the function in a convenient form to calculate its value. There are different approximate methods to represent the function in a convenient form, so that it can be calculated easily. In all these approximate methods, the basic technique used is to express the function as a linear combination of some base polynomials. Here we will discuss one of the methods which are very popular and which is very useful to express the function in Taylor series. To build the Taylor series for a given function, we will require interval where the function is continuous. Suppose the interval is x0 and xn. In this interval, the function should be a continuous function of x. Next, we need some base value a which is in this interval, and this base value is a constant value of x. Suppose we say this base value is a. The function should be known at this base value a, and all its derivative, all the derivatives of the function should be available or may be calculated at this base value. Then near this base value a, for any x in the interval, the function can be defined by using the Taylor series. You can see on your screen the Taylor series for function f x at base value a is given by equation 1. You can see that the Taylor series is infinite series, and we cannot handle the infinite process by using the finite methods. So, what we need to do is we need to truncate the Taylor series after a finite number of terms. If x is close to a, the series sum will converge after a finite number of terms to desired accuracy. This we can use to calculate the function in using some definite procedures. You can observe that in Taylor series, the base function used is, or rather the base polynomial is used is x minus a raised to k, where k is 0, 1, 2, 3, 4, 5, etc. And of course, the coefficients are the kth derivative divided by factorial k for the kth coefficient. The infinite series cannot be calculated. So, what we have to do? We have to truncate the series after a finite number of terms. Suppose we take n plus 1 terms of the Taylor series, then we can approximate the function in two parts. One part is a Taylor polynomial of degree n, and other part is the remainder term. So, you can see on your screen the expression 2, the equation 2, where the function is represented as sum of the Taylor polynomial and the remainder term, which is the truncation error in our calculation. Pn is the Taylor series polynomial, and it is a polynomial of degree n, and En is the remainder term which represents the error in our calculation. The Taylor series polynomial of degree n is given by equation 3, where we have restricted ourselves up to n terms in the Taylor series expansion given in equation 1. The remainder term of course can be calculated by using the remaining part of the Taylor series, and we just estimate the error in our calculation by using this remainder term. You can see the remainder term in equation 4, and here the s is some value of x in the interval x to a. To estimate the maximum error in our calculation, what we can do is we can just use the maximum of the function derivative n plus first derivative of the function, our interest, that means the given interval x0 to xn. So, if we take some value m, which is maximum of the n plus first order derivative of x in the interval x0 to xn, the maximum error can be represented by equation 5. Now, on your screen you can see some of the Taylor series expansions for the common functions. You can see the sin x, which is expanded in form of Taylor series around x is equal to a is equal to 0, cos x, which is also expanded around x is equal to 0, e raised to x, which is also expanded around a is equal to 0. You can, to explain the expansion, just take the example of e raised to x. Here the function f x is equal to e raised to x. Therefore, at x is equal to 0, the value of the function is 1. Since the function is f x is equal to e raised to x, all its derivative will be e raised to x itself. So, all derivatives calculated at x is equal to 0 will give you a value 1. Therefore, in Taylor series expansion, all derivatives and the function values are substituted as 1. Remaining part is of course the powers of x, because x minus a is equal to x since a is equal to 0. So, you can see that it is very easy to write the Taylor series expansion as given in table on your screen. Now, we will explain the evaluation of function by using the Taylor series expansion by an example. Consider the example of calculating e raised to x using Taylor series expansion. This expansion is around x is equal to 0, and suppose the function is defined in the interval 0 to 1. We want to calculate the value of the function at x is equal to 0.5. Suppose we terminate our series after 15 term and calculate the sum with increasing number of terms. On your screen you can see the table where we have given the sum of the terms with increasing number of terms. You can see that after say 6 terms, the series sum will converge up to 5th place of decimal. After 10 terms, it will converge up to 8 or 9 places of decimal, and after 14 terms, it will converge up to 14 places of decimal. We can also calculate the error by using the equation 5, and here we have the 16th order differential of the function, and that will again be e raised to x. To estimate the maximum error, we will calculate s is equal to 1. That means, we will take the e raised to 1, and that is always less than 3. So, we take the value of n plus first order differential of the function calculated in the interval as 3. X raised to 16 upon 16 factorial can be calculated by using a recursive procedure, and finally, we get the error in our calculation as 2.2 into 10 raised to minus 18. So, you can see that our result up to using only 15 terms will be accurate up to 17th decimal places. So, if we want to calculate the function accurate up to 16 decimal places, we can terminate the series after 15 terms. Now, some concluding remarks about the Taylor series. First is that the base function, base polynomial used to develop the Taylor series is x minus a raised to k. The second thing is that the x value should be near the base value a, and we can use a finite number of terms to calculate the function. The third thing is that to develop the Taylor series, we should know the function value and all its derivative at the base value x is equal to a. Now, suppose the function expression is not defined, it is not given to you. Rather, the value of function is given at discrete values of independent variable x. That means, we have a tabulated representation of the function with discrete values of x and the corresponding values of function, say y is equal to f x. We want to calculate the function from this information. So, the straightforward thing will be to fit a polynomial through these points. So, we want to approximate the given tabulated data by a polynomial. Using this method to evaluate the function from the tabulated data is called interpolation. The interpolation can be done for two different type of tabulated data. One is the tabulated data at regular interval and other is the tabulated data at irregular interval. In today's lecture, we will discuss the tabulated data at regular interval. For example, we will consider 7 data which is tabulated from x0 to x6 at regular interval of x and that interval is suppose h. The corresponding value of y is given by y0, y1, y2 etc. as given in the table below. The difference between two consecutive x values is of course h. So, what immediately we can do is find out the difference between the y values. So, if you find the difference between two consecutive y values, we will call it first order difference, and this difference is represented by delta 1 y k for the kth data in the range 0 to n minus 1. The differences of first order can be tabulated in the table, and next step is to find the difference of these first order differences. These differences will be called second order differences, and the second order differences are represented by delta 2 y k for k ranging from 0 to n minus 2. The value of these differences are given by equation 1 for the first order difference for all the x values starting from x0 to x6. The first order differences are given by equation 1. The table on your screen gives you the idea of how the differences will be calculated. The first order differences are calculated from the y values, the second order differences will be calculated from the first order differences, the third order differences will be calculated from the second order differences and so on. So, if you have n plus 1 data, you can have nth order difference in your difference table, that will be only the last value in your table. Expression for second order difference are given by equation 2. You can see this involves 3 values of y. Similarly, we can find the differences of higher order, and the final difference will be of course, if you have n plus 1 data, the last difference will be the nth order difference. We know that if a polynomial can be fitted through this data, it will be a polynomial of degree n, and if you differentiate the polynomial of degree n times, you will get a constant value, and if you differentiate the polynomial of degree n plus 1 time, you will get a value 0. So, if your data in the difference table gives you nth order difference as constant, you can say that the data is represented by nth order polynomial. We will use this information to frame a polynomial of degree n which passes through these n data values. So, the trial polynomial can be written as you can see in equation 3 on your screen. We will write a trial polynomial. This form is used for easy evaluation of the coefficients say a0, a1, a2 etc. So, we write the trial polynomial, and this trial polynomial will pass through all the data in the table of data given for evaluating the polynomial. So, as the polynomial is passing through all these data, we will start from the first value and we will say the polynomial will pass through x is equal to x0, correspondingly the y will be y0. So, if you substitute f x is equal to y0 and x is equal to x0 in equation 3, you will see that all terms in the expression apart from first term will become 0. So, you will immediately get the first coefficient a0 which is equal to y0, and it is represented by equation 4. Now, since the polynomial will pass through the next data point also, which is x is equal to x1 and the corresponding value of y is y1. If you substitute x is equal to x1 and the corresponding value of function is y1, if you substitute this value in equation 3, you will see that only 2 terms will be there in the expansion, and on right hand side all the other terms will become 0 because of the factor x minus x1, which will be 0 for x is equal to x1. Now, this expression can be used to calculate the coefficient a1. After some simplification, we will find that the coefficient a1 is the first order difference divided by h as given in equation 5. The same procedure can be followed for x is equal to x2, x3, x4, and we will see that the value of x substituted as x2, x3, x4 will give us the coefficients x2, x3, x4 in the form of the differences from the difference table. On your screen you can see the expression for A2, the equation 2, we see that the term in the square bracket for the expression of A2 is nothing but the second order difference of y0. So, what we can do, we can write the coefficient A2 in terms of the difference from the difference table, and that gives you A2 is equal to delta to y0 by 2 factorial h square. Similarly, using the value of x3, x4, we will be able to get the value of the coefficients A3, A4, etc. Since all these differences are nothing but the numerical values, so we can calculate the coefficients A0, A1, A2, A3, these are now the numbers, and using these numbers as coefficients of the polynomial in expression 1, we can write the Taylor series expansion, and this is given in equation 11. The equation 11 is called Newton's forward interpolation formula. By changing the function variable, this formula is having the differences and the powers of h in the denominator. So, we can do some simplification, and for this what we do, we change the variable and we write the variable u is equal to x minus x0 by h as we have defined in equation 12. Now, using this new variable, we can write x minus x1 by h as u minus 1, x minus x2 by h as u minus 2, and so on. We can rearrange the terms in equation 11, and we will write the factors as x minus x0 by h, x minus x1 by h, and so on. So, we can replace these factors x minus x0 by h, x minus x1 by h by the new variable u minus 1, u minus 2, etc. So, doing this rearrangement of the variable, we will get a convenient or rather more simplified form for the Newton's formula, and this is given in equation 13. So, the Newton's formula for new variable u is given in equation 13, and this is popularly known as Newton-Gregory formula for forward interpolation. A similar formula can be obtained by defining the polynomial with x values starting from the bottom of the difference table. In defining equation 11, we have started from the top of the difference table, and all the differences are relative to y0. You can see in equation 13, we are having the differences delta 1 y0, delta 2 y0, delta 3 y0, and so on. But we can construct a difference table which starts from the bottom, and there the differences will be delta 1 yn, delta 2 yn, and so on. These differences are called backward differences because they will start from the bottom of the table. So, what we can do, we can write a similar formula as in equation 11, but we will start the trial polynomial from the bottom of the difference table. So, in equation 14, we write the trial function with coefficients a0, a1, but the multiplicative factors as x minus x n, x minus x n multiplied by x minus x n minus 1, and so on. So, the coefficients are now calculated by substituting x is equal to x n, x is equal to x n minus 1 repeatedly up to x is equal to x 1. We can see that substituting x is equal to x n, we will get the coefficient a0 which will be equal to y n. In place of y0 in the forward formula, we are getting a0 is equal to y n in this formula. Similarly, we will get the a1, a2, a3 all in form of the differences from the bottom, and these differences, as we have already discussed already specified, are called the backward differences. The numerical value of forward difference and backward difference is not different, the only difference is the difference of notations. So, by using these coefficients in the expression 14, we will get another formula. This formula represented by equation 15 is called Newton's backward interpolation formula. Here again the values, the factors are divided by h square and so on. So, again what we can do, we can change the variable and the variable is transformed to u is equal to x minus x n by h. In place of x minus x 0 by h in the forward formula, here we use u is equal to x minus x n by h. Using this new variable, the polynomial in equation 14 can be represented by another simplified form, another convenient form, and this form is very much similar to the form of the equation 13. Now, this formula, the formula 15 which we have obtained by using the backward differences, is called Newton's backward interpolation formula. Now, in the expression of the interpolating polynomial, we have terminated the polynomial after n terms. The function can be approximated by infinite series, therefore, the remaining part of the function expression will go as error. So, error in the Newton's interpolation formula is given by equation 16, and here xi is a variable in the interval x 0 to x n, and this is taken as such that the n plus first order derivative of the function in the interval x 0 to x n is maximum. This gives us the allowed error, or rather this gives us the estimate of the error in the Newton's interpolation formula. We can see that if you change the variable, the error formula will be given by equation 17. The error in the Newton's interpolation formula will depend of course on the derivative of the function, n plus first derivative of the function, and of course the closeness of the x value to the other values x 0 x 1, that means on the interval. In today's lecture, we discussed the calculation of function by Taylor series expansion. The truncation error may be estimated by limiting the infinite series to a finite polynomial. We also estimated the error in the Taylor series. We discussed the interpolation of tabulated data at regular interval and derived Newton's interpolation formula. We also estimated the error in Newton's forward interpolation formula. Hope you enjoyed the lecture.